Hello everyone, my name is Jason Gregerson, and this video is going to be an introduction to the matrix equation, AX equals B. In this video, we will investigate the equation AX equals B and relate it to some previous ideas. We're also going to observe the properties of matrix multiplication. So first, let's introduce the matrix equation. Given some matrix A, which is an m by n matrix, and a vector B, our question is there an x such that AX equals B? This is the matrix equation, and x would be a solution to this matrix equation. Now, another way we can also ask this question, and maybe a more challenging way, is given a matrix A, is there an x such that AX equals B for any B in Rm? Recall that if A is an m by n matrix, if A is an m by n, then x must be an n by 1 vector, and the resulting B would have to be m by 1. That's just to do the multiplication. But now it's more than just having the right dimensions to do the actual multiplication. The first part says that if we have a specific B, is there an x where AX will equal that B? And the second part says, is there a solution no matter what B is? So those are really our two questions. So to answer those two questions, let's look more closely at the multiplication. So if we write out that equation AX equals B, showing some of the components, and here I'm just going to use a 2 by 2 matrix and a 2 by 1 vectors to demonstrate this process. But if I start out, here's my matrix equation. But if I actually do this matrix multiplication, I know that one way I can multiply A times X is in terms of a linear combination technique. And I would write out that multiplication by saying x1, that first component of my X vector, times the column, the first column of A, plus x2 times the second column of A. That would still be equal to that right-hand side of B. But once I write that out, I recognize that this is just a vector equation. And so asking, is there an x1, x2, is there a vector x that satisfies this matrix equation? Is there a solution to this matrix equation? It's saying the same thing as, is there a solution to this vector equation? And this vector equation is just asking, is there a linear combination of these two vectors that result in B? And another way we can say that is by saying, is B in the span of these two columns? So those are all the same kind of questions. If there's a solution to the matrix equation, there must be a solution to the vector equation. But I've worked with this vector equation before, and I could simply multiply both of those columns by those scalars x1 and x2, and then I could add the two vectors, and I could combine and say those two vectors are equal if and only their components are equal, and the net result would be two different equations that look like this. That would be my first equation. My second equation would be a 2,1 x1 plus a 2,2 x2 equals b2. And when I look at that, I say, wait a second, this is just a linear system. So asking if there are solutions to the matrix equation or the vector equation is also saying the same thing as, is there a solution to this linear system? And if I wanted to solve that linear system, I would know how to do that. My first step would be to write out the augmented matrix A11, A12, B1, and A21, A22, B2. And I would take that augmented matrix and put it into the row reduced echelon form. So what I can see now is that all these statements are the same thing. Asking if there's a solution to the matrix equation is the same thing as asking if there's a solution to the vector equation, which is the same thing as asking if there's a solution to the linear system. And to do any of those things, all I have to do is take that augmented matrix and row reduce it. So all these things are very related. So because they're related, I can generate a set of theorems based on this. And so first we're going to write out these theorems, and then we're going to discuss each point. So given some matrix, some m by n matrix A, then the following statements are either all true or all false. So in other words, having one of these statements true will imply the rest. So the first statement we're going to say is, there is always a solution to AX equals B. So that's our first statement. So now we're saying that if there's always a solution to AX equals B, regardless of what B is, then these other statements must also be true. Then each B in Rm is a linear combination of the columns of A. And so these two things apply each other. So if B was a linear combination of the columns of A, that's exactly stating out that basically what that vector equation is just telling us. So if there's a solution, if B is a linear combination of the columns, then there's also a solution to AX equals B and vice versa. So those two things apply each other. The third thing that would be in this group is that the columns of A span Rm. And once again, this is looking back at the definitions. If there's always a linear combination that will get me to B, no matter what B is in Rm, then the set of all linear combinations of these columns must be all of Rm. That's exactly like saying that the columns of A span Rm. So once again, these are just applying the definitions once we realize that all these equations are the same. And the last one says that A has a pivot position for each row. Now this one's a little bit different. This one might stand out a little bit. How does having a pivot position in each row of the matrix A somehow tell us that there are solutions for the matrix equation and the vector equation and the linear system? Let's take a closer look at that. Let's take some sort of A. So I'm going to write my A matrix 1 0 0 0 1 0 0 0 0. And I'm going to augment it with the B vector B1 B2 B3. And so the idea here is, let me just add one more 1 in the bottom corner here, and now I have a pivot position for each row of the matrix A. And from here I can say my solution is just B1, B2, B3. No matter what that B vector is, no matter what B1, B2, B3 values are, there is always a solution to AX equals B. And I can see that solution directly. Now, if there was not a pivot position in each row, for instance, if that was a 0 there, now I don't have a pivot position in each row of A, there would only be a solution to the system if B3 was not equal to 0. If B3 was any non-zero value, then this far right column would be a pivot column, and therefore there would be no solutions to the system. So, to guarantee that there's a solution for any B, I would have to have a pivot position in any row. So now that we've seen all the relationships between these different kinds of equations and what their implications are, let's do a practice problem. So here's our practice problem. It says let U equal this vector, the vector 0, 4, 4, and let A equal this matrix. And the question is U in the plane spanned by the columns of A? And once again, we're going to have lots of different questions that follow the same process for answering them, because there's so many relationships between these different equations. So this question is U in the span of the columns of A? So what does it mean to be in the span of the columns? It means I could take some linear combination of those columns and get to U. If there exists an x1 and x2 that make this a true statement, then U would be in the span of the columns of A. But as soon as I write that out, I recognize that as a vector equation. And what we just saw with this vector equation is the same thing as this matrix equation. which of course is the same thing as an associated linear system. And all of those can be solved by putting my information into an augmented matrix. That augmented matrix would look like this. And to find solutions to the linear system or the vector equation, the matrix equation, I simply put this into row echelon form. So for me to put this in row echelon form, first thing I'm going to do is take that third row and move it to the top row. Now I don't necessarily have to do that. I could simply turn this top left corner into a 1 by dividing through that first row by 3. But if I do that, I'm kind of going to get a lot of ugly fractions. So it might be a little cleaner if I just move that bottom row to the top. I'm certainly allowed to do that as a row operation. Now my next operation, I'm going to leave that first row the same. And to eliminate this 3, I'm going to take row 2 minus 3 times row 1. The result will be 0 here. I'll get negative 5 minus 3 times 1 is negative 8. 0 minus 3 times 4 is negative 12. Then I want to put a 0 here. I want to eliminate this value. To do that, I'll take row 3 plus 2 times row 1. Negative 2 plus 2 times 1 is 0. 6 plus 2 times 1 is 8. And 4 plus 2 times 4 is 12. My next step is I'm going to eliminate this position. To do that, I want to say row 3 is equal to row 3 plus row 2. So row 2 will stay the same. Row 3, 0 plus 0 is 0. 8 plus negative 8 is 0. And 12 plus negative 12 is 0. So now I have it into this form. As I look at this, this looks to be R, E, F. And once it's in row echelon form, I can see that that far right column is not a pivot column. It's not a pivot column, which tells me that there are solutions to the linear system, which means there are solutions to the matrix equation, which means there are solutions to the vector equation, and all those things finally answer my question. So I know that yes, U is in the plane spanned by the columns of A. Now, of course, if I wanted to go farther, I could finish up this row reduction and put it into reduced row echelon form and find the specific weights where I would take that linear combination to get to 0, 4, 4. That would be a simple enough process if I just finish this out and put it into reduced row echelon form. I encourage you to do that on your own. And that concludes this video on matrix equations. Thank you.